In the pursuit of personalized learning experiences, high school timetables must adapt to accommodate students' diverse interests, strengths, and weaknesses. Modular curricula have become increasingly prevalent, but the scheduling process remains a significant hurdle. Existing tools often group students by similar interests, neglecting individual preferences. To address this, advanced algorithms can be employed to optimize timetables based on students' unique profiles. This involves integrating assessments of their interests, aptitudes, and learning styles into the scheduling process. By doing so, personalized learning experiences can be tailored to each student's needs, enhancing engagement and academic performance. The paper extends the XHSTT format to incorporate two new constraints, enabling flexible student course choices and class formation requirements. This extension addresses recent research on timetabling demands in Central European schools, where students are increasingly expected to follow their individual interests. Unlike traditional formats, this new formulation allows students to choose their own courses with alternatives or preferences, enhancing the adaptability and satisfaction in their educational paths. The introduction of individuality into high school timetables is crucial, particularly with the extension of the XHSTT format to accommodate recent trends in student course choices and class size requirements. This involves the need for an extension to the XHSTT format to include constraints that reflect student choices and class size balance. The new constraints are categorized into student choices, class size requirements, and class size balance. The student choices constraint ensures that students with similar profiles are scheduled together, while class size requirements are encoded using existing constraints. The extension aims to be as small as possible while accurately encoding the new constraints, ensuring it only includes useful constraints for those creating timetables. Managing student course choices in high schools is a complex task, as students may not attend all selected courses due to scheduling conflicts. Two common methods are employed to address this issue. The first involves creating a timetable and then allowing students to choose lectures that fit their schedules. The second approach involves students providing priorities for their choices, and the timetabler attempting to fulfill those priorities. The authors propose a novel approach, integrating graph theory and integer programming to optimize student course allocation. They formulate the problem as a maximum weighted independent set problem, where each course is represented as a node in a graph, and edges connect courses with conflicting schedules. The weight of each node corresponds to the number of students enrolled in the course. The authors develop an integer programming model to solve this problem, incorporating constraints to ensure that students are not assigned to conflicting courses and that course capacities are respected. The model is solved using a branch and cut algorithm, which provides an optimal solution. The authors evaluate their approach using real-world data from a high school, comparing it to existing methods. The results show that their approach leads to a significant reduction in scheduling conflicts, with an average reduction of 34.6% in unfulfilled course requests. A key advantage of this approach is that it allows for the incorporation of additional constraints, such as teacher availability and room allocation. The authors also discuss limitations, including the need for accurate data on student course preferences and the potential for computational complexity. Future work includes exploring the application of this approach to other educational institutions and integrating it with existing timetabling systems. Overall, the author's novel approach provides a promising solution to the complex problem of managing student course choices in high schools. The student choice constraint is a novel constraint introduced to regulate resource allocation in event scheduling. This constraint applies to each resource that is either a direct child of the resources node or part of a resource group mentioned in the resource group's child. Specifically, it enforces a minimum and maximum bound on the number of event groups that each resource must attend. Attendance is defined as visiting any sub-event of a given event group. The deviation of the student choice constraint is calculated as the absolute difference between the actual number of event groups attended by a resource and the specified minimum or maximum bounds. This deviation serves as a penalty for violating the constraint, encouraging the optimization algorithm to find solutions that respect the desired attendance ranges. By incorporating the student choice constraint, weighted preferences for resource allocation can be effectively encoded, allowing for more nuanced and realistic modeling of event scheduling problems. This constraint is particularly useful in scenarios where resources have varying capacities or preferences for attending different event groups, enabling the optimization algorithm to make more informed decisions. The class size problem is formulated within the XHSTT framework, where each instance consists of 4 components: times, resources, events, and constraints. Events are characterized by durations, specifying time slots to be assigned, while constraints dictate how these times are distributed across the week. The model incorporates 3 resource types: teachers, rooms, and individual students. For fixed classes, students are directly assigned to time slots. In contrast, dynamic courses involve creating 3 event types: a main event for time assignment, student resource events to ensure minimum student numbers, and hard constraints to prevent split assignments. This setup enables the solver to dynamically group classes based on scheduling and student preferences, guaranteeing that each course meets its minimum student requirement. By doing so, the model effectively balances student demand with resource availability, optimizing class scheduling and allocation. The introduction of individuality into students' high school timetables is achieved through a multi-step process. Initially, an event is created for each class, with each student assigned as a resource. Subsequently, student requirement events are generated for each student, representing their chosen subjects. These events are linked to the main events via hard link events constraints, ensuring that sub-events have the same time assignments as the main event. Hard avoid clashes constraints on individual students guarantee that each sub-event has a different student assigned, referred to as minimum requirement events. A second set of events, called maximum requirement events, is created, similar to the previous ones but containing optional students from the event perspective, allowing for flexibility in student assignments while maintaining constraints. To manage class size balance, a better approach involves creating separate courses for subjects with large student numbers, utilizing student choice constraints to ensure students can choose one of the courses. However, this may result in unbalanced class sizes. To prevent this, balanced class size constraints are introduced, which enforce a minimum and maximum number of students per class, thereby balancing class sizes. The research extends the high school timetabling problem by focusing on balancing class sizes across different event groups. It introduces a new constraint, balance class size constraint, aimed at minimizing the difference in assigned resources between event groups. This constraint is structured with tags like name, required, weight, cost function, applies to, maximum difference, and type. For example, it's applied to 2 equivalent math classes with a weight of 1 and a linear cost function, limiting the maximum difference in assigned resources to 2. The deviation is calculated as the difference between the event group with the most or least assigned resources and the allowed maximum difference. The paper also presents an ILP model to solve the extended problem, extending the formulation from Christensen et al. 5, by incorporating the new constraints and relevant variables and linkings. The full ILP formulation is detailed in the appendix, supporting linear and quadratic cost functions. The authors introduce the sets of entities relevant to the extended modular XHSTT problem, which are identical to those used in the original problem. These sets include T, an ordered set of times, Tg, a set of time groups, R, a set of resources, E, a set of events, e.g., a set of event groups, a set of event resources of an event E, Se, a set of sub-events of an event E, C, a set of constraints, P, points of application of constraint C, D, deviations of a point of application P, I, possible deviation values of deviations D, and J, possible deviation sum values at points pages. Additionally, the authors define further notation to express constraints, including road, a dummy resource with no resource assigned, TD, a dummy time with no time assigned, the duration of event E, DSE, the duration of sub-event say, E element of C, indicating a constraint applies to event E, R element of C, indicating a constraint applies to resource R, e.g. element of C, indicating a constraint applies to event group e.g. WC, the weight of constraint C, rho, T, the index of time T in the ordered set T, PR, a binary indicator of whether event resource has a pre-assigned resource, and BC, The upper and lower limits of constraints circa these sets and notations are essential in formulating the constraints and objective functions of the extended modular XHSTT problem, which will be discussed in subsequent sections. In the optimization problem for scheduling resources in quantum computing, additional variables and functions are introduced to model resource allocation and event scheduling. These variables include XSE, T, R, YSE, T, VT, R, WSE, R, B, CEG, R, SC, P, D, SC, P, D, I, U square sum, use, QR, T, and PR, TG, which represent resource assignment, event start times, and usage counts. Functions F, SC, P, D, CF sum square, and CF square sum are defined to calculate the cost of constraints, sum of cost functions, sum of square cost functions, and square sum cost functions, respectively. These functions are essential for evaluating the objective value of the problem and determining the optimal scheduling strategy. Some constraints have upper and lower limits, and the deviation value v is defined using the function UBC, BCV. This function is crucial for handling constraints with both upper and lower bounds, ensuring that the deviation does not exceed these limits. The precise modeling of these variables and functions is necessary to achieve efficient resource allocation in quantum computing, highlighting the complexity of resource scheduling and event planning. The updated objective function for introducing individuality into students' high school timetables is presented, consisting of the sum of all cost functions of individual constraints. This function is split into separate values z hard and z soft to denote the costs of hard and soft constraints, respectively. In comparison to the objective function by Christensen et al., this function is extended by adding terms describing the deviation of new constraint types. The objective function is formulated as a minimization problem, where the cost function f is a sum of 15 terms, each corresponding to a specific constraint or penalty term. These terms include costs associated with student assignment, time assignment, event splitting, distance between split events, resource preference, time preference, avoiding split events, spreading events, linking events, avoiding clashes, unavailable times, idle times, cluster busy times, limiting workload, balancing size, and student choice. Linking constraints are introduced to connect variables WSE, R, and B, R, ensuring that the number of students assigned to an event does not exceed the capacity of the resource. Two additional constraints link variables CEG, RTOBE, R, ensuring that the number of students assigned to an event group does not exceed the capacity of the resource. A balance class size constraint is also introduced, applying to event groups, to ensure that the class size difference between event groups does not exceed a specified parameter BC. This constraint considers only resources of a specific role in the event, if specified. The student choice constraint is introduced, applying to resources and evaluated at the resource point of application. This constraint is formulated using parameters BC and BC, denoting the minimum and maximum values specified in constraint C element of C. Mathematically, it is represented as n array summation, E element of EG, element of E, R element of R equals RC, is less than or equal to S student choice, C, R, for all C and C, RC element of C. To address model size reductions, the authors eliminate variables that would never be used for an acceptable solution. Specifically, they eliminate variables XSE, T, R, and WSE, R for students R that did not select an event E, say element of E. This means that students who did not select an event are not assigned to one of its subevents, which is supported by practice. Furthermore, the authors only generate subevents with a feasible duration if there is a hard split events constraint restricting the duration and/or amount of generated subevents. This technique is similar to the one used by Fonseca et al. To reduce model sizes. The authors evaluate their model using a benchmarking set of 18 high schools with modular school systems from 6 different federal states in Germany. This diverse set is chosen to reflect the variability of secondary educational systems in Germany, depending on the particular federal state. The instances used are available at Insert Location. In the realm of high school timetables, introducing individuality is a complex task. This page delves into the introduction of such individuality, focusing on the Austrian company Untis GmbH's anonymized instances. These instances have been translated into the new extended XHSTT format, paving the way for more instances in the future. The XHSTT instances do not directly match with the original Untis instances due to the intricacy of Untis specification. To provide insight into this, Tables 1 and 2 offer statistics describing resource usage and modularity of each instance. Factors like the number and type of constraints, student pool size, and restrictive times for events and teachers significantly impact these statistics. The primary objective is to comprehend the complexities involved and plan for future extensions with more modular schools across Europe. This endeavor aims to enhance our understanding of the intricacies of high school timetables and how they can be optimized to cater to diverse needs. In the provided table, we observe the distribution of resources across new instances in Germany, encompassing events, students, classes, teachers, and rooms. Each instance is uniquely identified, revealing varying amounts of these resources. This data serves as a crucial foundation for understanding the modularity of these instances, which is further quantified in another table. The modularity metrics include choice constraints, balance constraints, and required events, offering insights into the complexity and flexibility of these instances. These metrics are vital for optimizing resource allocation and instance management, as they provide a comprehensive understanding of how each instance functions within the system. By examining the distribution of resources and modularity metrics, researchers can identify patterns and trends that may influence the efficiency and effectiveness of resource allocation strategies. This information can be used to develop more targeted approaches to managing resources, ultimately enhancing the overall performance of the system. Moreover, this data can serve as a benchmark for future studies on resource distribution and modularity in similar contexts, allowing researchers to compare and contrast different approaches and outcomes. As such, it is essential to maintain the technical accuracy and depth of this content, ensuring that the refined version retains the critical details necessary for expert researchers and stakeholders. The evaluation of the Individualized Learning Plan, ILP, for high school timetabling is a complex problem, particularly with the introduction of new constraints. To address this, the authors executed 18 instances using a commercial ILP solver, Gurobi, with a memory limit of 64 GB and a time limit of 6 hours per instance. The results indicate that out of 18 instances, solutions were found for only 10, and the obtained solutions did not meet the criteria for a viable school timetable. This highlights the intricacies of the problem and the limitations of current methodologies. The study suggests potential for progress by integrating ILP with meta-heuristic or matheuristic approaches and emphasizes the importance of balancing computational resources with research accessibility. The table provided shows the results of applying the ILP model to various instances of modular high schools in Germany, categorized by region. Each entry details instance variables, constraints, and objective values. Despite running for 6 hours, the ILP model failed to find satisfactory solutions, indicating the need for more efficient methods. Future work proposes using ASAT Solver to assess the problem's hardness and explore new cuts for the ILP model. Additionally, evaluating the performance of existing heuristics and searching for new ones is intended. In this research extension, the authors aim to introduce individuality into students' high school timetables by leveraging a more adaptive large neighborhood search (LNS)-based approach. This approach integrates methods from reinforcement learning to enhance the process of finding optimal schedules. The development will be supported by providing additional benchmark instances from across Europe and a publicly available tool for validation. The authors will also compare future findings with actual school timetables to identify any gaps between theoretical and practical solutions. This research builds upon previous work in timetabling, including the integration of matheuristics and metaheuristics, Fonseca et al. 2016, Integer Programming Techniques for Educational Timetabling, Fonseca et al. 2017, and Hybrid Local Search-Based Solvers for High School Timetabling, Da Fonseca et al. 2016. The authors draw upon a comprehensive set of methodologies and tools to refine their approach. The lanes-based approach allows for greater flexibility and adaptability in scheduling, which is crucial in addressing the diverse needs of students and teachers. By incorporating reinforcement learning, the system can learn from past experiences and adjust accordingly, leading to more efficient and effective timetables. Moreover, the use of benchmark instances from across Europe ensures that the approach is tested on a wide range of scenarios, enhancing its generalizability and applicability. The publicly available validation tool will enable researchers and practitioners to evaluate the effectiveness of their own timetabling solutions, fostering collaboration and improvement in the field. Ultimately, this research aims to bridge the gap between theoretical and practical solutions in high school timetabling, providing a more adaptive and effective scheduling system that caters to the unique requirements of each student and teacher. The authors provide a comprehensive integer linear programming (ILP) formulation for the modular educational systems model, building upon the notation and variables introduced in Section 3. This ILP formulation comprises a set of constraints that ensure the integrity and feasibility of the solution. Constraint 52 links the variables SC, P, D and SC, P, D, I, indicating that the sum of deviation indicators for each course, period, and day must equal the deviation indicator for that course, period, and day. Constraints 53 and 54 ensure that only one deviation indicator can be set per deviation and that the variable U square sum C, P, J represents the squared sum of deviations, respectively. Similarly, constraint 55 ensures that only one deviation indicator can be set per point of application. Constraint 56 links the variables SC, P, D and U step sum C, bounding the step sum of deviations by the maximum allowed deviation. The ILP formulation also includes constraints 57 and 58, which ensure that each subevent is assigned exactly one starting time and that the number of assigned resources equals the number of event resources. These constraints guarantee that the solution satisfies the resource allocation and scheduling requirements. By providing the complete ILP formulation, the authors enable the exact computation of objective values, ensuring the accuracy and reliability of the model's results. This precise ILP model allows for a detailed analysis of the educational system's scheduling and resource allocation, providing insights into potential improvements and optimizations. The research introduces a novel approach to personalizing high school timetables through an optimization model. It enhances scheduling efficiency and flexibility by introducing new variables and constraints. Key variables include VT for resource availability, WSE, R for subevent resource assignments, and R for event start times. Constraints ensure correct subevent assignments, valid start times, and sufficient time for subevent durations. The model also defines subevent activations based on start times and resource allocations, aiming to balance resource utilization and personalized learning paths. This approach could potentially improve academic performance and student satisfaction by introducing individuality into timetables. The research focuses on the constraints and parameters used in the study. It begins with the assign resource constraint, which applies to events and specifies the point of application as the event resource. The assign time constraint is also detailed, applied to events with the point of application as the event. The split events constraint is discussed, including parameters for minimum and maximum event amounts and durations. The distribute split events constraint is also covered, with parameters for minimum and maximum numbers of subevents and their durations. Each constraint is explained in detail using precise language and technical terms for accuracy and clarity. The constraints for introducing individuality into students' high school timetables are crucial for optimizing the scheduling process. These include prefer resources, prefer times, avoid split assignments, and spread events. Each constraint is designed to address unique needs and preferences, ensuring a personalized schedule for every student. The link events constraint applies to event groups and is evaluated at the event group level. It introduces binary variables O, T and leg, T, indicating whether at least one subevent of event E or event group EG is scheduled at time T. Equations 86 and 87 set O, t to 1 if any subevent of E is scheduled at time t, and 0 otherwise. Equation 88 links O, t and leg t, ensuring that if any event in event group e.g. is scheduled at time t, then leg t is 1. Equation 89 enforces the link event constraint, bounding the difference between leg t and O, t by the slack variable slink event c, e.g., t. The order events constraint applies to pairs of events and is evaluated at the pair of events level. It introduces variables h_first e and h_last e, representing the first and last time assigned to any subevent of event e. Equations 90 and 91 update h_first e and h_last e based on the scheduling of subevents say at time t. Equation 92 enforces the order event constraint, bounding the difference between h_last e and h_first e by the slack variable s_order_event c, e. The avoid clashes constraint applies to resources and is evaluated at the resource level. Equation 93 ensures that the binary variable vt r is set to 0 if resource r is unavailable at time t, and 1 otherwise, to avoid clashes. The avoid unavailable times constraint, also applied to resources, is evaluated at the resource level. Equation 94 ensures that the sum of qt r over all times t equals the unavailable times for resource r. These constraints are crucial in modeling the event scheduling problem, ensuring that events are linked correctly, ordered appropriately, and do not clash with unavailable resources or times. In the realm of high school timetabling, introducing individuality to students' schedules is paramount for optimizing resource allocation and minimizing idle times. To achieve this, binary variables are employed to indicate events before and after specific times, as well as identifying idle periods. A key constraint in this process ensures that idle times are limited, with parameters bc and bct specifying the minimum and maximum values. The constraints detailed in equations 95 to 104 focus on two primary objectives: limiting idle times and ensuring events are scheduled efficiently. These equations form the backbone of a system designed to optimize time usage, allowing for better allocation of resources within the educational environment. By implementing these constraints, educators can create more personalized and efficient schedules for their students, ultimately enhancing the learning experience and maximizing productivity. This approach not only benefits students but also teachers, administrators, and the overall educational system, as it promotes a more streamlined use of time and resources. In the resource allocation problem, 4 constraints are introduced to ensure feasible and optimal resource allocation to events. The limit busy times constraint, denoted by equation 105, restricts the total busy time of resources in a cluster to not exceed a specified limit, applying to resources and enforced at the resource level. The limit workload constraint, represented by equation 106, confines the total workload of a resource within a specified range. The workload of a solution resource is defined as the product of the duration and load of an event resource, denoted by we, say, This constraint also applies to resources and is enforced at the resource level. The balance class size constraint, composed of equations 108 to 110, ensures that the difference in class sizes between two event groups does not exceed a specified maximum class size difference. This constraint applies to event groups and is enforced at the event group level, utilizing the variable MRC, e.g., to denote the number of resources allocated to an event group. Lastly, the student choice constraint, although not explicitly defined, also applies to resources and is crucial in the resource allocation problem. These constraints are essential in ensuring that the allocation of resources to events is feasible and meets the specified requirements, guaranteeing that resources are allocated efficiently and effectively. The incorporation of individuality into students' high school timetables involves introducing parameters for minimum and maximum values and constraints. This is achieved through the use of parameters BC and BCT, which denote these values in the formulation. The addition of binary indicators ensures that the ILP solver uses the appropriate constraints based on assignments, mitigating the issue of deviation variables. This approach allows for the creation of valid and optimal schedules while considering computational time. Accurately modeling constraints is crucial for achieving the best objective values. The NeuroEvolver framework, a novel approach to efficient and scalable neural architecture search, leverages evolutionary algorithms to navigate the vast search space of neural network architectures. By representing neural networks as fixed-length binary strings, the framework enables efficient mutation and crossover operations. Task-specific operators, tailored to the problem domain, further augment this encoding scheme. Through extensive experiments on benchmark datasets, the authors demonstrate NeuroEvolver's effectiveness, showcasing significant improvements in model accuracy and search efficiency compared to state-of-the-art methods. Notably, NeuroEvolver discovers novel architectures that outperform manually designed networks, requiring fewer computational resources and evaluations. The framework's mathematical formulation details the encoding scheme, mutation and crossover operators, and the fitness function guiding the search process. Figure 1 illustrates the iterative process of population initialization, selection, mutation, and crossover, as well as candidate architecture evaluation. Table 1 provides a comprehensive comparison of NeuroEvolver with existing neural architecture search methods, highlighting its advantages in terms of search efficiency, model accuracy, and adaptability to diverse problem domains. While the current implementation has limitations, including the need for further search space exploration and improved optimization techniques, the authors outline future work directions, such as applying NeuroEvolver to real-world problems like computer vision and natural language processing, and integrating additional evolutionary operators and search strategies. Overall, NeuroEvolver offers a promising solution for efficient and effective neural architecture search, with potential implications for developing more accurate and efficient machine learning models.